Hello, I'm Frank. In this video I will review the exercise Reflectance Spectroscopy of Martian Analogs. You can find this exercise on my website frankstutorials.nl. The exercise is a puzzle where you have to match rock samples to rock descriptions by interpreting the mineralogy from infrared reflectance spectra. So it's a great exercise to learn about spectral interpretation of minerals. Right, let's start. Okay, what you see here is the table that you had to fill out. And in this table you can find rock descriptions of 13 rock specimens that you have to match to codes that are shown on the photographs in this exercise, or that you can also see on rock samples themselves. Yeah, so what you have to do is you have to interpret reflectance spectra with the same code, and then depending on the result of the minerals that you have interpreted, you can relate that to any of the rock descriptions. You should also use your geological rock recognition skills, because some of the spectra are a bit ambiguous, and some of the minerals, they're not really diagnostic. Okay, so let's start with the first rock in the table, which is a talc schist. Well, if you look at all the different rocks in this exercise, then there are a few foliated rocks, so a few schists, and one of them is this one, which is a bit grayish, greenish. It is actually quite soft. It has a waxy luster, so that's an indication of talc. Another foliated rock would be this one, a greenish one, but that's not what normally talc or talc-bearing rock looks like. So let's start with this one. It has the code FVR02. So what we'll do, we'll use Hippie hyperspectral Python software, and we open the spectral library viewer, and then I open the unknown spectrum FVR02 and plot it together with a known spectrum from the USGS spectral library of talc. Right. Let's do it. Okay, let's do it like this. This is what we get then, the result. In green is the USGS spectrum of talc, and in blue is the unknown spectrum of FVR02. And if you compare the two, you can see that there is a good match, especially here near 2310 more or less, which is related to a magnesium hydroxyl bond, and that's typical of talc. So this peak matches. There is some minor feature here which matches to this feature, and then we have another feature here, a slightly longer wavelength that matches. Also this feature at 1.39 approximately, that also matches. Yeah, so with these matches we can be quite certain that this is indeed talc. We can also plot a continuum removal, or we can do a continuum removal and look at the result, and then you'll see that the features match quite well here, as discussed before, here and here. Only in the visible near infrared we see some differences, but that probably has to do with the color of the rock and also the ion content. So this talc schist probably has some ion, and that results in this deep feature here at 1 micrometer. Okay, so that is the first match we have. So write down the code here. And then we continue to the next one, which is also a schist, Fuchsite, quartz schist. Fuchsite is a chromium-bearing muscovite. So it has a spectrum similar to muscovite with, in this case, a feature near 2200 nanometers. I showed you this foliated rock already before. Well, this is typical. The color is typical for Fuchsite. So yeah, this is a good candidate to be the Fuchsite quartz schist. It has a code FVR01. I think I made a mistake. This should be FVR02, of course. Yes. So, and this is FVR01. So I'll plot this one together with muscovite. No hull removal. And then we get this these two spectra. Yeah, at first glance you can already see that there is probably a good match. These features match. These two match to these two features. The green spectrum has a little bit more water. And then we have this feature here at the 1.410 that matches. Now we can see it better if we do a continuum removal, and then we can see that the match is actually quite good. The only difference is really in the visible wavelength range. You know, the blue spectrum, which is the unknown spectrum, has a peak at around 525 nanometers. Yeah, and that can be explained by the green color. Yeah, because 500 something nanometer is the wavelength of green light, and this rock is green. So that's why we have this typical pattern here. Right. Then we go to the next sample, which is a hydrothermally altered rhyodacite tuff that contains pyrophyllite. Well, if you look at all the different rocks, then there's one rock that really looks like a clay-bearing altered rock. It's this one. Yeah. So what we're looking at here is a volcanic rock that has been completely altered. The matrix is highly siliceous, and the phenocrysts and lithic fragments have been completely altered to a white powdery mineral. Yeah, so likely to be pyrophyllite. So let's have a look. FVR05. Plot that together with the pyrophyllite spectrum. First, no hull removal, and then this is what we get. Well, I think this looks like a very good match. The general shape of the reflectance spectra are quite similar. The unknown spectrum has lower reflectance values. Okay, it's probably less pure. And then we have a good match here at 1.4 or 1.39 something. Then we have a good match here at 2.166 more or less, and that's typical of pyrophyllite. And that way, using this feature, you can also differentiate it from muscovite, for instance, because muscovite has a feature at slightly longer wavelengths. And then there is a difference in the depth of the water feature. So the unknown rock has more water in the rock than the pyrophyllite from the USGS spectral library. Let's see what it looks like if we do a continuum removal. And then we can see even better that there's a good match. You can see that there's an almost perfect match of the features. Okay. Right, let's fill out that in the table. Yep, we're making good progress. The next rock is a rock which is metamorphic. It's a crystal tuff, so volcanic rock. It's from the Duffer Formation in Western Australia. And it contains chlorite. And the type of chlorite, well, is characterized by the absorption feature of the magnesium hydroxyl feature, which is at around 2338. Well, if we look at the different rocks, then there are two candidates that are chlorite green, and that could be volcanic. That's this one, BJ0435, and BJ 04014. So let's look at those two in the spectral library viewer. So these are the two unknown rocks, and then I'll open that together with chlorite. And then we get this. The USGS spectrum is red. It has slightly higher reflectance, and the green and the blue, they're from this rock sample set. Okay, we can already see that there are some match. This is typical for chlorite, an iron hydroxyl feature and a magnesium hydroxyl feature, OH feature here. Okay, a strong slope here because of the reduced iron in the mineral. Well, we want to compare the spectra in more detail. Okay, then we get this. Now I would like to zoom in here, because what is diagnostic, or what we should use to differentiate between the different types of chloride, is the wavelength position. And we can see that the blue one has a wavelength position at 2324 more or less, so that is relatively short. And the other one, the green one, has a feature at 2339.38. That means that the chloride in the green spectrum is more iron rich, because the higher the iron content, the longer the wavelength position of this feature. And the other one is more magnesium rich. Now let's have a look at the table again. So the green one is 0.35. Yeah, so that coincides with this feature. So that's BJ 04035. So that is this one. That's the metamorphic crystal tuff containing chloride. And then let's see where the other chloride bearing rock is. That is here. That's a metamorphic high magnesium basalt. Yeah, so it has more magnesium, so therefore a lower aluminium hydroxyl wavelength position of the magnesium hydroxyl feature, and that's this one. Yeah, so metamorphic high magnesium basalt from the Archean. And like all these rocks from the Pilbara, they have this reddish coating of iron oxides. But we're not measuring the surface. Yeah, that surface. So we have measured a relatively fresh cut. So we can put the code in here as well. Good. And then we continue to the next one, which is a metamorphic rhyolite. Yeah, so this is also a volcanic rock. It's also metamorphosed, but not foliated. Well, we do have a few candidates. So we have two metamorphic volcanic rocks left. And that's this one, the BJ04147. And the BJ 04043. And here you can see very nicely the volcanic texture with the phenocrysts. It's probably not a rhyolite because doesn't contain enough silica. This one is more silica rich. And if you look at the texture carefully, you can see that there is some boxwork in here. So where likely feldspar phenocrysts have been weathered out. Okay, so let's check this one first. But we can also, well, let's also at the same time look at this one. So what we'll do is I'll show the two spectra of these rocks together with muscovite. And then we'll see what we get. The metamorphic rhyolite should have a shorter wavelength position of the aluminium hydroxyl feature than the other one, which is the metamorphic dacite, which has a longer absorption wavelength of the aluminium hydroxyl feature. Okay. Okay, this is what it looks like. The reflectance spectra have much lower values. Of the unknown spectra, they have much lower values. So the rock, well, is also a bit darker, but also probably the muscovite content is relatively low. But you can see that the absorption features are there, though very faint. In order to to compare this better, we'll do a continuum removal, and then we'll see this. You can see that the hydroxyl feature here at about 1.4 coincides very nicely, and then we have this feature to around 2.2 coincides, and then we have two other features here that there where we can also see a match. So I think we can be certain then that the mineral in these two unknown rocks is muscovite. But we want to differentiate between the two different rock types based on the wavelength position. And then we see this. The green rock has a wavelength position which is shorter, which means that the aluminium content of the muscovite is higher at 2194 approximately. And the other unknown spectrum is longer at 2213, 12 more or less. So this information now we can use to fill out the table. This one is then the longer wavelength, which is the 033. Yeah, that's this rock. And then the shorter wavelength is the rhyolite. This one. It's the BJ04. 147. Okay, so we have solved that as well. Then we continue to another rock, which is a banded chert. It's sedimentary. It's a precipitate from the Archean. It's a mixture of minerals consisting of chert, of course, chalcedony, and there are some other minerals in there as well, like siderite and muscovite. Well, if we look at the rocks, then there's only one banded rock that would qualify as a banded chert. That's this one. Maybe that is FVR03. Maybe this could also qualify for a layered sedimentary rock TZ04, but this is more like a chert. So let's compare this spectrum to that of chalcedony, but also with siderite, because those are minerals that could potentially be in there. So the green rock is the unknown rock. Can't see a very good match, except for the water feature here. But for the rest, there's quite a bit of differences between the blue and any of the other two. Maybe continuum removal will help. Not really, except for perhaps this feature, which could be because of carbonate. It is almost similar to that of siderite, but not completely. So in fact what we can say about this spectrum is really not conclusive, and really you need to use your geological rock recognition skills to match this one. Okay, but it's not difficult. Because it's clearly a banded chert. Let's go to the next one, which should be a dolomite. This will be the rock, or is it here, that is sedimentary, and that could potentially be a dolomite. It is also from the Archean in Western Australia. And let's see if we can find any traces of dolomite in the spectrum. So this is the unknown spectrum. And let's compare it to dolomite here. We plot the two. Well, let's not do a continuum removal. This is what we get. this doesn't make it very clear, so we'll do continuum removal. And then what we see, there's quite a bit of differences between the spectra, because it's not a pure dolomite, this rock. But it does have a dolomitic feature here, 2.308. Yeah, so, and also the shape is somewhat asymmetrical, so I think we get a somewhat positive match here. It's not very convincing, but yeah, we can call this a dolomite. So that's TZ04. The next one is a gypsum. Well, if you know what gypsum looks like, it's not very hard to match it actually, because well, this is typical gypsum. It's transparent, a bit whitish, vitreous luster. Yeah, quite typical gypsum. So we can enter that straight away, I would say. There's no doubt, but still, gypsum has a very typical reflectance spectrum, so we may as well see if that one how it compares to the USGS spectrum of gypsite, of gypsum. So plot them together. You can see that the general shape of the two spectra are not so similar. But if you look at the absorption features, then you find good indications that indeed there is a good match. Yeah, especially this deep feature at the 1.4 something that matches, and then there's another feature here and there's another feature here. So these three features are very typical of gypsum, and you find them here also in the unknown spectrum. This feature here at around 1.74 is also typical of gypsum, and it occurs with some variation in other sulfates as well. But you can see that it's also present in the unknown spectrum. Then there's a feature at 2.212 more or less. Yeah, that's also matching. Yeah, so because of this, we can be quite sure that we have a very good positive match. Continuum removal shows basically the same, except for a feature here, which is not explained by the USGS spectrum, and that may be because of some clay mineral which is present in the rock, and it's also visible from the rock itself. Yeah, there are some traces of clay on it as well. Good. That was FER04. Then we have three left. One is an hydrothermally altered rhyodacite tuff, which is contains vuggy quartz. It's from the rhodocheilar epithermal gold deposit, and it contains alunite as the spectral mineral that we want to match. Well, if we take rock number FVR06, this is a siliceous rock. It contains vugs because of dissolved rock fragments, crystals, and it also contains some brighter and flash chlorite alteration minerals, which could be an indication of alunite. So let's have a look. I'll show the spectrum together with the alunite spectrum. Well, alunite has a very typical reflectance spectrum. You have the deepest feature at around 2160 something. Matches quite well. There's a smaller feature on the right hand side in this feature that also matches. There's another feature here at 2.322 that matches. This feature here, sulfate feature at 1.760 matches to this one, and then very typically a duplet around 1.4. Which also matches. Yeah? So we can be quite certain that this is indeed alunite. we can compare the two spectra by removing the continuum, and then we can see an even better correspondence. Yeah, so this one is a positive match. We can enter it in the table. And then we have two samples left. One is an olivine nodule in a volcanic bomb. Well, if you have once seen an olivine nodule, you know what it looks like, and it looks like this. Yeah, so this is part of a volcanic bomb with some volcanic material here in dark, and this is a xenolith of olivine-bearing rock, so a rock fragment that was extruded together with the lava, and it has this typical greenish color. Yeah, so we do not have to verify the spectrum to be sure, but let's do it because we can learn from it. So that is FVR07, and I'll plot that together with, where is it? Here, olivine. And then we get this. The spectra are continuum removed, and you can see that the spectra of both the unknown spectrum of the unknown rock and olivine, they both have this deep absorption feature at around 1 micrometer, and then a few smaller absorption features. So let's remove the continuum removal, and then we get this, and you can see that the two spectra also, the reflector spectra themselves, they also match quite well. Yeah, and this is this deep feature at 1 micrometer is really the feature that scientists use to map olivine-bearing rocks on the surface of Mars. Okay, so this is also a positive match. Then there's one left, which is the pyroxenite, which contains the low calcium pyroxene enstatite. And there's also one rock specimen left, which is FVR08, which is this. It's a dark rock, large crystals that are intergrown. It's heavy, it's a dense rock. So there are all suggestions, well, at least the texture is an indication for an igneous rock, and the density is an indication of a pyroxene rich rock. And let's have a look at the reflectance spectrum and see how that matches with an enstatite spectrum. Yeah, this is what we get. Yeah, the overall shape looks quite similar. So let's do a continuum removal, and then we get this. A feature at 1 micrometer varies a little bit. That may be because of the slightly different composition. This feature matches quite well, and another feature at 2.317 also matches quite well. Yeah, so although again not diagnostic, this one, I think we can still talk about a somewhat positive match here. So we'll enter this one here. Okay, so I think we have now solved the puzzle. So that's the end of this video. I hope you found it useful. I hope you learned something from it. And I thank you for watching. Goodbye. Now it's time for some more coffee.